Welcome back, folks. We're playing the same game. We're figuring out the complex relationship between the voltage across a capacitor and the current through that capacitor, and we're going to call that the impedance of the capacitor. All right, so let's get to it. And let's start out with a sinusoidal voltage source, and we're going to put that across a capacitor, just like this. Okay, plus and minus, we're going to have our known voltage across it, and we're interested in figuring out the current through it. And it's going to have some capacitance C, and some fun things happen with this one. And then the same fun things are going to happen with the inductor, but backwards, because that's what they do. They're backwards. Same thing, but backwards. Okay, so V of t, again, is a cosine omega naught t plus our phase angle theta. And that's in volts. And we want to go find I. So we got to think back to the capacitor equation, right? I of t is equal to C dV of t dt. All right, so we can use that capacitor equation. I said it relates to voltage and current, and it does, but we would like to do it with a complex number if we're constraining ourselves to sinusoidal signals. And that's what we're doing. We're saying, well, it's not some arbitrary voltage, it's a cosine. So what can we do with phasors to make our lives a little easier? So the first thing we got to do is take the derivative of this voltage. So you got to go back to Calc 1 for this one. And we say the derivative is, well, let's see, the derivative of a cosine is a negative sign, right? A is a constant. I'm going to leave a little gap here, and we get sine omega t plus theta. Okay, and I left that little gap because we have to use the chain rule, if you remember from Calc 1. So I've got to take the derivative of the stuff inside with respect to t. Theta is a constant, so that's going to drop out. And the derivative of omega t with respect to t is just omega. So omega is going to pop out in front here. Okay, so I have the derivative of the voltage is negative a omega sine omega t plus theta. So that's the first thing we need up here. And then we can rewrite the current. We can say negative a omega c sine omega t plus theta. Okay, that's not a c, that's a bracket. How to make that clear from that one. Always trying to improve my handwriting, especially with this fancy tablet. Okay, so, oh, that's not in volts. You would have yelled at me in class, right? That's in amps. It's a current. Okay, so we have the voltage, we have the current. We want to figure out the relationship between the two, and we're going to call this Z sub C, right? The impedance of the capacitor, in this case, is the voltage divided by the current. Okay, so let's go grab that voltage. Being a lazy engineer like I am, efficient. An efficient engineer, right? So we take that voltage, and then we're going to divide by the current, and the current's right up here. Volts over amps equals ohms. Okay, so the unit of impedance is still ohms, if we think about that. All right, from here we got to get a little tricky, because we, in the previous one with the resistor, we had the same cosine in the numerator and the denominator, so they just canceled and they went away and life was good. But now we have a cosine up here and a sine down here, but we know about phasors, and we can use phasors to make this happen, which is magical. It's fantastic. You could possibly do it with trig identities, but I'm going to question your sanity if you even try that. Okay, so whoops, stay right there. So we're going to take Z sub C, and A is in the is a coefficient, right? And then we have cosine omega t plus theta. So if I want to take all of this and turn it into a phasor, okay, so I'm going to take this chunk, and I'm going to use the phasor transform, right? The magnitude of that phasor is 1. I'll do it in orange. Okay, and the angle of that phasor is theta. So we have 1 at an angle of theta. Done. The frequencies are the same, so we can do this, right? If the frequencies were different, we'd have to use all those trig identities and hope for the best. So down here we have negative a omega c, and I'm going to take this. Ooh, I got to convert that to a phasor. Didn't we just have a video on this? How do I take a sine and rewrite it as a cosine? So the first thing we're going to do is say, hey, this is equal to cosine omega t plus theta minus 90 degrees. Okay, if we take that cosine and we shift it by negative 90, it's going to be equivalent to that original sine. So I'm going to rewrite it that way, and then when I take that and turn it into its phasor, it's going to be 1 at an angle of theta minus 90 degrees. Okay, I didn't quite leave myself enough room. And we should put some brackets in here just so we make sure we keep that angle together. Okay, 1 at an angle of theta minus 90 degrees. That's pretty cool, huh? Okay, so we can continue doing some math with this, and it's starting to get a little more compact, but now it's complex. Okay, and that's kind of the nature of the beast. We're going to use complex numbers to make it a little smaller, but more, well, complex. Okay, let's see, what can we do? A is going to cancel A. Let's just get rid of that now. We could wait, we could not wait, but we're going to end up with 1 over negative omega c. Okay, we're going to pull all of that out, and then I'm going to look at this phasor division. So if you watch the review videos, or if you're just a complex arithmetic aficionado, as I am, when we divide two phasors, it's easiest in polar form. Well, it's a good thing we're in polar form here. We're going to divide the magnitudes, and we're going to subtract the angle of the denominator from the angle of the numerator. So dividing the magnitudes, let's see, we got to get all this up in here, right? So dividing the magnitudes, we're going to have 1 divided by 1. I can do that one in my head. Okay, and the angle in this case is going to be the angle of the numerator minus, and we got to be careful with distribution, the angle of the denominator. Okay, so we haven't done braces yet. Let's use braces. I'm sure there's a mathematician cringing somewhere in the offing. Okay, but we have 1 at an angle of whatever this reduces to. And let's not lose track of our coefficient. Okay, so 1 divided by 1 is 1. Theta minus theta is, well, the thetas drop out, and then that negative distributes over here. So this is going to be 1 at an angle of 90 degrees. Okay, so we're getting there. We're very close. 1 at an angle of 90 degrees. That's in polar form. What is it in rectangular form? So I want you to picture this. Thusly, real, imaginary, and 1 at an angle of 90 degrees. So it's going to be 90 degrees pointing straight up, and it's going to have a length of 1. Okay, so that's 90 degrees and a length of 1. So we have another name for that. We can say that 1 at an angle of 90 degrees is equal to J. Okay, Everybody else in the world is going to say I'm an electrical engineer, we use J. So that's just J. That's it. So we can substitute that in right there. Oh, that's behind me. I'm sorry. Hopefully you were looking at the image that I've posted. Okay, I think I fixed the corrupting images problem with a lot of hassle. Okay, so we plug in J, and that ends up in the numerator. So J over negative omega C. So that's one form we're going to see it in. It's good times. But if we invert J and bring it down, we can also say that that is equal to 1 over J omega C. And actually, more often than not, you're going to see the negative up there. Okay, you might see one or the other, but they're equivalent. We'll probably start off with this one, but as you move forward in your classes, this one's going to become more relevant. And that's the payoff. That's the impedance of the capacitor. So let's see here. That's what we want to take away. What's interesting about the capacitor is that the impedance is now dependent on the frequency. Okay, with the resistor, we didn't have that. Omega didn't show up in the impedance anywhere. But now we have omega as part of the impedance, and that's going to do some wonderful things, and that's going to do some horrible things. The wonderful thing is we can use it to build filters. So if we want to tune in a radio station, we can do that with capacitors. If we want to get rid of noise on a power supply, we can do that with capacitors. The horrible thing that happens, because the impedance is dependent on the frequency, is that we can use it to build filters. Okay, sometimes you build filters when you don't mean to, and if we're trying to pass a high frequency signal, say through a network cable, we're inadvertently building a capacitor by putting two wires near each other. And that capacitance may begin to filter the signal and limit how quickly we can change the state of that bus, and that's going to affect the digital bandwidth of the signal that we can pass. Okay, so this is simultaneously a wonderful thing and a horrendous thing, but we've got to understand it so we can use it to our advantage and avoid it when it's a disadvantage. Okay, we got to do the same thing with the inductor, and then I'll sum it all nicely up in a table for you. Good stuff. Next one's the inductor. Stay tuned and good luck.